Good afternoon and welcome to this introduction / walkthrough of Hardy-Weinberg equilibrium. Our subject for the day is this little squishy blobfish to the left. We will be exploring its varying skin colors and their respective alleles and genotypes. So what is Hardy-Weinberg equilibrium and what are the assumptions? Hardy-Weinberg equilibrium is constant or an unchanging population in terms of genetic variation. This occurs when the following 5 assumptions are met. Number 1, an infinitely large population. This means that there is less chance for outside disruptions to shift allelic frequency with greater individuals. For example, a natural disaster that kills 10 subjects in a population of 100 versus 10 subjects in a population of 20. 10% of individuals with varying genotypes may have passed away in the first population, while 50% passed in the second. Number 2. Random mating. This is the antithesis of assortative mating, which means that individuals are more likely to mate with mates similar to themselves. Over time, the heterozygous genotype would be less prevalent. Number 3. No selection. This means simply that no individuals have advantages over others. They can't get evolutionarily ahead. Number 4. No migration. This accounts for a locked set of allele types. In other words, no new allele types can join the population and no allele types can leave. Number 5. No mutation. Mutations are the key to increasing genetic diversity, therefore they cannot exist in an unchanging population. At the bottom, you can see that I've written out the Hardy-Weinberg equation. We will apply this in the following slides. Here are our blobfish that will be representing the population we will study. 1,000 hot pink blobfish, 700 regular pink blobfish, and 50 baby pink blobfish. Before selection, we can calculate their allelic frequency and genotypic frequency. Allelic frequency is easy because we add up all the individuals who are homozygous big P plus half of the heterozygous individuals to get the allelic frequency of the big P and then divide by the total population, and vice versa with the small p. Genotypic frequency, on the other hand, requires us to plug in our allelic frequencies into our Hardy-Weinberg equation, as you can see written out in our genotypic array. Assuming that now the selection is in play and the second assumption has now been broken, we will start to see changes in genotypic frequency. Ecologists found that the hot pink blobfish were less likely to be eaten by predators because it matched their environment more so than the baby pink blobfish. This is exemplified in the fitness level shown on the slide. The homozygous big P or hot pink blobfish have the greatest fitness in their environment, whereas the baby pink blobfish have the least. So after the selection has occurred, we can calculate their average fitness and later their affected genotypic frequency. Average fitness is simply initial frequency times fitness for every genotype added up. This results in 0.885. Frequency after selection is then calculated by initial frequency divided by average fitness. The resulting values have changed to favor homozygous big P or hot pink blobfish, which we expected. Therefore, in the far future, we may predict that only the hot pink blobfish will survive selection.